Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Stepping aside as we jump into section 3.5 in the Big Ideas Math Integrated Math 1 textbook. This is graphing linear equations in slope-intercept form. Guys, we've been waiting for this one. This is here, y equals mx plus b, and graphing without use of a table. This is one you'll be using for your future, for your children, for your grandchildren, and generations beyond. I mean, it's a nice, quick example of something for you to say, look, Ma, this is something I can do, and it even has fractions, and I'm good at it. And I hope we can all do this one together. Now, this section, I don't know what the problems look like. Obviously, they're going to ask you to graph some, but then they're going to have word problems, and then they're going to have a how do you see it question, and then error analysis, and your friend argument, whatever. So a lot of different questions at play. See what it is that you need to see out of this thing. Otherwise, try it for yourself, please. I'm going to attach graph paper in the description section down below alongside the PDF for this particular section. And you can find the block of certain problems you want in the problem set and the timestamps, because I'm going to begin with the lecture portion. And away we go. We're going to find the slope of a line. Yes, sir, we're going to. We're going to use the slope-intercept form of a linear equation. That's the one that we've been seeing so many times. And use slopes and y-intercepts to solve real-life problems. It'll solve its own problem for you to be able to graph equations using slope-intercept form. I see the phrase rise here, which is great. I'm going to be using that as well. I'm also going to be using the word fall. It's just the opposite. I think rise, I think up. I think fall, I think down. So just keep that in mind with this. Now, that, again, up versus down. When you hear run, by default, that does mean run to the right. If I need to say run the other direction, I'm going to be saying run left. Okay, I want to make sure that you understand that, because this rise and run concept is all what slope is about. That's all what slope is about here. Slope-intercept form is the name of the equation y equals mx plus b. We'll talk about more as to why that is and how we use it. And a constant function. I don't know. We'll see what that's all about. Independent, dependent variables were previous terms. Let's go ahead and get started. The slope m of a non-vertical line passing through 2 points x1, y1 right here. Say that's some point and some point x2, y2. Is the ratio of the rise change in y to the run change in x. Okay, all they're saying is, you go from one point to another. They can be any point in space, in time, that kind of thing, right? I could have $1 billion right now, but then over the course of the next 3 years, I make $20,000, right? Or I could have no money, and over the course of the next 3 years, I make $20,000. That's the same rate no matter where you started from, and no matter, what year it was and things like that. It's still the same rate. So we're just comparing where two values are to each other, right? Not to, say, the origin, not anything like that. So they talk about this rise over run. How much do you go up versus how much do you go to the right? Because, again, same thing, right? You could go to your friend tomorrow and you say, dude, I made $100. And they're like, dude, that's sweet. But you're like, yeah, man, I made $100 over the last 2 months. They're like, oh, well, that's not really much, right? It's not just the rise. It's not just how much you earned or what you did or, whatever. It compares to a certain amount. And generally, it's in a word problem, it's involved with time, right? But not always. Anyway, so what you have to do is you have to find that rise and that run. How far do you go from one y value to the next? And how far do you go from one x value to the next? And it's calculated. The distance between two numbers is the difference between those two numbers. So you see a formula right here. It says y2 minus y1 divided by x2 minus x1. And these aren't y squared and y to the first power. That's a specific y value versus another specific y value, right? We subtract one from the other. We subtract an x from the other. If I asked you how far 3 and 5 were from each other, it's 2. But you can calculate that by doing 5 minus 3, right? Or if I said how far are you from 1 to 10, 10 minus 1 is 9. So you can come up with the distance by calculating the difference. And it's even true of negative values. Distance is still difference in those scenarios. Subtracting a negative becomes addition, but it initiates as subtraction. Now, slope is the definition of this, right? To me also, it's like the steepness of the line, and I mean that's calculated that way, but basically, the larger the number in your division, the steeper that slope is going to be, right? Steepness is dependent on how much you do rise compared to a run of some other people. Now, the letter we use is m, and yes, it is the same m we use in y equals mx plus b. I might be teasing that a little too early, but just so you understand, they do use the letter m for slope. You might ask why. I think I looked it up once. It probably has to do with the Latin version of the word slope or something. It's kind of like mountain. It's like mountain in Latin. So let's just go with it. When the line rises from left to right, the slope is positive. Notice they do say from left to right. That's why I talked about run being the run to the right. As you run to the right, are we going up or are we going down? Oh, look, they use the word fall as well. When the line falls from left to right, the slope is negative. So, hey, yeah, guys, when we do a subtraction of two numbers, right, we do this number minus this number, we get a positive. This number minus this number, we get a positive. And positive divided by positive is a positive number. But if you go downward instead of upward, you're subtracting maybe this value from that value, and the result's negative, right? What's this? How far do you go from 8 to 2? You do 2 minus 8, you get negative 6. So you fell 6 instead, right? You fall 6, and negative divided by a run to the right positive is a negative slope. And I want to make sure that it totally makes sense, right? When we say, how do you determine whether slope's positive or negative? Like, what's a positive slope? And a lot of people will just say, it's when it goes up. To that I say, all of them go up and down, right? All of them go up. All of them go down. Like, look at this one. This one goes up right here. This one goes up right here. They all go up, except for horizontal lines. But they all go up and they all go down. This one goes down. This one goes down. So you have to be more specific. It's when you go up as you go to the right. When you go down as you go to the right, the slope is negative. Anyway, spending a lot of time on this first part with the slope, but I should be, right? This is the first very important part for what we do. Now, we will look at the examples of this as well and how they calculate it. I do want to mention, because I don't know how they're going to do all the equations here, or the slopes. I do want to mention that if you're given the graph, you don't have to calculate the slope. You can also count the values in the slope, the difference in y and difference in x. But let's look at how they go about it. We'll confirm that those counts are what they're supposed to be, and we'll go from there. Okay. The line rises from left to... Oh, hold on. What was the question? Describe the slope of each line, then find the slope. So I think based on description, they're trying to describe whether it's positive or negative. In this case here, they're saying this line rises from left to right, so the slope is positive. Yes, as it goes right, the graph, it goes up. The line goes up. So that's a positive slope. Versus part B, this one, as the line goes right, it goes down. So that's a negative slope. Now this goes down as it goes left, but that's kind of like a negative over negative, which is positive. We'll get to a bunch of those. And this also goes up as it goes left. That's positive over negative, right? So as it goes to the left, that's a negative run. That's running to the left. Anyway, let's go ahead and calculate that slope. They go from the point -3, -2 to the point 3, 2. So consider this an x2 and an x1. Consider this a y2 and a y1. We're going to do a subtraction of that sort. The slope is y2 minus y1, 2 minus -2, divided by x2 minus x1, 3 minus -3. Now, subtracting a negative turns into addition. So 2 minus -2 is 2 plus 2, which is 4. 3 minus -3 is 3 plus 3, which is 6. 4, 6 reduces to 2/3. We are not going, outside of word problems, no slopes will be written as decimals, and no slope word problem even will be written as a mixed number. We are going to leave them as fractions, even improper fractions at that. Case in point, look at example B. This one, y2 minus y1, they're taking -1 and subtracting 2. -1 minus 2 is -3. Over x2, let me move my face. Over x2 minus x1, x2 is 2 minus x1 is 0. 2 minus 0 is 2. -3 divided by 2, it doesn't reduce. They just wrote it as -3/2. And it's an improper fraction. Guys, leave it as an improper fraction. Don't change it to -1.5. Do not change it to -1.5. No reason, no value. The slope, this will be fine. This will be fine. Now, before we move over to the other problems, I want to read some of the things that they state here in case I state the same thing. And then I want to talk one more thing about those problems, or a couple more things about these problems, really. It says when finding slope, you can label either point. Oh, perfect. This is one of the things I was going to say. You can label either point as x1, y1, and the other point as x2, y2. The result's the same. So what if instead of this being x1, y1, what if this was x2, y2, and this one instead was x1, y1? Now, when you do that subtraction, we're going to say y2 minus y1 over x2 minus x1. And we get -2 minus 2, which is -4. Wait, Mr. Robinson, last time they got 4. -4 and 4 aren't the same thing. No, they're not. But this also becomes -6. And a negative divided by negative becomes a positive. So that becomes positive 4 over 6, or, when reduced, positive 2 over 3. So it's still the same slope no matter which way you do it, as long as you go the same direction, right? If I do this y2 minus y1, then I better do x2 minus x1. I cannot do this minus this and then this minus that. You'll get an opposite slope from what you want. That's like saying, I'm running 6 to the right, but I'm going down 4. No, you're not. If you're going to the right, then you're going up. Or if you're going down, then you're going left, right? It depends on the direction that you flow. And because they had us describe it to begin with, even if you mess up on that calculation, fix it. If I accidentally do, 3 minus -3, get a positive 6, and that becomes a negative 2/3, and say, oh, wait a second, but I knew the slope was supposed to be positive, then heck, just turn it positive, right? You made a mistake, and you're addressing it. Don't stick with your mistake in that way. Okay, they mentioned this part here. I mentioned this as well. This says x sub 1 and y sub... This is x sub 2 minus x sub 1, y sub 2 minus y sub 1. These are known as subscripts, as they say. Not superscripts. Those are like exponents. These are subscripts. You will just hear me say y2 minus y1 over x2 minus x1. It takes way too long to say y sub 1, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. The last thing I want to state here that I don't know if they're going to talk about it later or not, because yes, we do have to calculate them, especially if points are way out of window range, if they don't give you a graph or you have weird decimals. But if I have the graph, guys, I can count these numbers. So from here to here, how much do we run? 1, 2, 3, 4, 5, 6. You can count it without needing to calculate it. And how much do you rise? 1, 2, 3, 4. So those are those numbers 4 and 6 as well. I don't know if they happened to count based off that fact, or obviously the calculations here, but you can kind of do an either or there. Now in the second example, same thing. How much do we run? To the right, we run 2, that's positive, and we go down 1, 2, 3. The fall of 3 is what makes that thing negative. Now the last thing I want to mention here, and it has to do with the negative slope thing, and I've addressed this in several chapters already, mostly in chapter 1, I believe. When you have, because they wrote this negative 3 halves here, right? When you have a negative fraction, where does the negative get applied? Does it get applied to the top, like negative 3 over 2? Does it get applied to the bottom, like 3 over negative 2? Or does it get applied to both, negative 3 over negative 2? Well, the answer is either of these are fine. Either of these are fine. This one's not. We just actually saw that a negative 4 over negative 6 actually turns into positive 2/3. So here's an example of that one. Right? Negative 4 over negative 6 equals positive 2/3. Negative 3 over the negative 2 would be positive 3 over 2. A negative fraction means one is the negative or the other is the negative, and you can actually apply both of these in a way that helps you with the slope. If I said the 3 was negative, that means I'm going down 3 as I go positive 2, right 2. If I had the 3 as the positive, I could say I'm going up 3 as I'm going 2 to the left. So I can go 2 left, and I can go 3 up that way and do the same count that way. It's still the negative slope. Up and left, down and right are both negative. Anyway, I'm living very much a long time on this, right? Almost 13 minutes into this, and I'm still on the first page of these notes, so I'm going to go ahead and progress forward. Finding slope from a table. The points represented by each table lie on a line. How can you find the slope of each line from the table? What is the slope of each line? Well, values in a table represent points on a graph. There's a point here that's 4, 20, a point here that's 7, 14, 10, 8, and 13, 2. If they all lie on the line, any 2 points can be chosen to represent the slope. Whether I choose these two together, or these two together, or these two, or, I'm trying to do it, or these two together, no matter what, we should get the same slope because they all lie on the same line. They all have the same rate of change. That's what they say. Choose any 2 points from the table and use the slope formula. So they chose 420 and 714, the first two. They can do y2 minus y1 over x2 minus x1, 14 minus 20 over 7 minus 4. And this is an example, right? They don't have the graph. So maybe you don't count it, right? You don't draw a graph just to count it out. Do the subtraction. Do the subtraction. Or I could ask you, how much do you go from 20 to 14? Now you have to be careful, because if you say 6, well, it should be negative 6. From 20 to 14, you go down 6, and that's what makes the 6 negative in that case. Now, from 4 to 7, you would say, plus 3, right? So minus 6 and plus 3. The subtraction does that as well, right? 7 minus 4 and 14 minus 20. But if that's too much to do the formula, work what you work out. Now, anyway, negative 6 divided by 3 is negative 2. When I stated that you can't have any mixed numbers, negative 2 is a whole number. That's fine. You can write it. But keep in mind that also means negative 2 over 1. It's a good reminder, especially when we do the graphs ourselves. Part B, there's no change in y if you choose any 2 points. I don't know which ones they choose. Let's see. They chose negative 1, 2 and 5, 2. There's no change in y, so when you do y2 minus y1, 2 minus 2, you do get 0. And 5 minus negative 1, remember, turns to 5 plus 1, which is 6. But 0 divided by 6 is still 0. The slope is 0. Now, we don't see what that looks like as an actual line yet. But imagine what that is. When the y value is always 2, guys, that's a horizontal line. What that's telling you is a slope of 0 is a horizontal line. For this one, there's no change in x this time. So when you choose your 2 points, whatever y2 minus y1 is, yeah, right, it becomes some number. But x2 minus x1 actually becomes 0. What happens when you divide 6 by 0? We mentioned before, you can't divide by 0. The answer is not 0. The answer is undefined. Literally that word. Division by 0 is undefined, so the slope of the line is undefined. So there are 4 different types of slopes that we've now run into. Positive, negative, 0, and undefined. If no change in x, that's a vertical line. That's another instance of us seeing that, vertical line fails its own vertical line test. It's not a function. Its slope is undefined, right? You can't write this in y equals mx plus b form, that kind of stuff, and we're going to get more into that. So this vertical line has a lot of bad things going for it, but when we determine its slope, we say it's an undefined slope. For a lot of reasons, but yeah, undefined slope. Oh, here we go. Didn't even see this. Listen, I should learn to know that the book is going to address what we need. Positive slope, it goes up as it goes right. It goes down as it goes right, negative slope. It doesn't change its height. It doesn't change its rise. It doesn't change its run. Okay. All right. Using the slope-intercept form of a linear equation, here we are. We are at our stage. It seems like we don't start with these problems, right? It seems like we start just by talking about slope only, determine types of slopes, look at them on graphs and tables. So y equals mx plus b is something called slope-intercept form. We've probably heard y equals mx plus b quite a bit. We've gotten in this form. We're going to keep doing it, and we're going to graph out of it without need of a table, because this thing is in such a form that y based on x uses the m and the b to find their points. The m represents the slope. We already know that. We're well aware. The b represents the y-intercept. Now, we just came off of graphing out a standard form, and we learned how to find a y-intercept from there, right? You set x equal to 0. So why does b represent the y-intercept in this one? Well, let's see. They're not really talking about it there, but the y-intercept, here it is. The y-intercept is the value of y when x equals 0. What happens in this equation when you substitute 0 for x? You get m times 0 plus b. M times 0, just like anything else, is 0, and 0 plus b is b. When x is 0, your y value is b. We actually saw this in our tables for our graphs. If you notice, anytime I went from like -2 to 2, -2, 1, and 0. Every time I said, hey, notice how the 0 wipes out this term and you're just left with this other term? Always. That's the y-intercept. That's where it crosses the y-axis. So we're going to do something based off these two sets of values, and we're going to be able to construct a graph like that pretty easily. We're going to be able to come up with points like that, even when the slope's a fraction, especially when the slope's a fraction. There's something known as a constant function as well. We just saw y equals b, but this one's literally for the equation of the line. This is when you have a horizontal line. So when the slope is 0, you have a horizontal line, and that's the reason, because the only y value that you can ever be the entire time is b. So we're going to see that. So let's look at some examples, parts A through C. Find the slope and y-intercept of the graph of each linear function. Now what we're going to do here, okay, we're not drawing the graphs yet, but find the slope and y-intercept. We have to recognize we're in slope-intercept form. So in y equals 3x minus 4, notice that we are in y equals mx plus b form. Y is by itself. X term is in front here, multiplied with this number. So that number 3 represents the slope. Your slope is 3. Your y-intercept plus b, and this says minus 4. I guess we're adding a -4. I'm not really going to directly write that specifically. I might say it. But b is your y-intercept is -4. Your slope is 3. Y-intercept is -4. Those are the identifiers. Now, part B says y equals 6.5. This is one of those examples of a constant function. The x term isn't there anymore, but that's because the m that affected the x term, the m was 0. M was 0. If m is 0, we can write it as y equals 0x plus 6.5. There's your slope-intercept form. We don't have to, but that helps remind you, by the way, we have to find out the slope. The slope was 0, and the y-intercept is 6.5. And that means it crosses at 6.5 and just goes horizontal like that the entire time. That's its thing. That's what it does. Now, the third one says -5x minus y equals -2. Honestly, it reminds me a lot of standard form. Remember ax plus by equals c? This looks a lot like standard form. But we want to get it in slope-intercept form, which means take that -5x, add it to the other side of the equation. But the y is still negative, so we have to divide everything by -1, which means a total sign change. 5x minus 2 becomes -5x plus 2. So this is slope-intercept form. Until you're in slope-intercept form, your values don't necessarily truly reflect your slope and your y-intercept. Case in point, well, that was -5, and it still is -5. But this was a -2. Now it's a +2. So your slope is -5 and the y-intercept is 2. Okay. By the way, because I talk about common habits that students have all the time, x just happens to be the number that multiplies by your slope. M is your slope and it's multiplying by x. Your slope is not -5x. That is incorrect. That is actually very incorrect when we consider certain word problems that we talk about. It's actually very incorrect. When you think of slope, you think of rate. I don't know if you do, but a slope is a rise over run. It's a rate of change over time. If I said something like, I make $30 an hour, right? I make $30 an hour, I make $30 an hour. Okay, the slope is 30. If I made $30 an hour for 20 hours, 30 times 20 is 600. Now, is my slope $30 an hour or $600 an hour or $600 period? The slope is $30 an hour. So if you say mx, -5x is your slope, you just said something like 600. That's not what it is. So it's way different. I'm over talking, over rambling. All right, guys, we're going to use the slope-intercept form to graph. We are actually going to now be able to do this. Sorry, I've been teasing it for over 20 minutes. Let's actually get into it. First of all, you have an equation like this that actually is standard form, once again, which we know how to graph out of, and we can actually confirm that this answer is what it is based off what we know from graphing out a standard form. But let's rewrite it in slope-intercept form, subtract 2x from both sides. That's the section we're in. Now, the slope is -2. The slope is -2. Now, the important part that we've seen from slope so far is slope has been represented as a fraction, a rise over run, or in this case, a fall over a run. -2 can be rewritten as a fraction. -2 divided by 1 is still -2, right? You want it as a fraction. You want it as a fraction because you want to know how much you change in y versus how much you change in x. Now, they call it a rise of -2, which of course means a fall of 2. So from a specific point that you know on your graph, every time you go down 2, you want to go over 1. You go down 2 over 1. Great. We're going to do that to plot every point here. Think about it. Every time x increases by 1, every time you go another 1 to the right, that's another -2 that's added to your overall set. -2 is added means that's another 2 that's subtracted. We're losing another 2 every time x goes by 1. Now, the one you want to start with is the y-intercept, though. Remember, the y-intercept is 2. That means there's a point on the graph that's 0, 2. This is where you want to start on your graph. That's your reference point. From there, we can apply our slope. And remember, the slope's -2, whether the y-intercept is at 2, or at 0, or at 6, or at -14. You still would go down 2, right 1, plot a point. Down 2, right 1, plot a point. And that's what I'm going to do, guys. I'm going to plot as many points as I can fit in my window range. That includes not just down to the right, but also up and to the left. If my slope is -2 over 1, that can also be written as 2 over -1, which means I can also go up to left 1. Hey, there's a point. Up to left 1. That continues my negative slope. Just because I go up doesn't make it negative. Or excuse me, positive. Going up and left makes it negative. Anyway, hey, you do the graph from there. Now, they did say identify the x-intercept. The x-intercept is the point where we cross the x-axis, and this one we can clearly tell what that one's going to be. It's crossing the x-axis at 1, 0, so the x-intercept there is 1. Don't make me forget to answer that part, but that is a feature that's on here. If you see where it crosses, name it. Now, one last thing before we move on to here. You know, we did graph this out of standard form in the last section. So what did we do at the time? We found the x-intercept by setting y equal to 0. That means the term goes away. You get 2x equals 2. Divide both sides by 2. You get x equals 1. The y-intercept, you would set x equal to 0. You would get y equals 2, and that would be the y-intercept. So you'd get this point here. You'd get this point here, and you draw the line through it. Guess what? It's the same line. I mean, it should be. It's the same equation. But in slope-intercept form, we represent it differently as far as what we use. We use the y-intercept, and it's there in plain sight. But this now represents the slope to find all of the points that you want. Now, we wrote it as a fraction. I want to remind you of that because I'm sure we're going to do ones that have fractions, and you're going to like them. You're going to be fine with them. Let me get a sip of water here. Or 4. Okay. Graphing from a verbal description. A linear function g models a relationship in which the dependent variable increases 3 units. For every 1 unit, the independent variable increases. Hey guys, independent is x, dependent is y. Every time we go up 3, we're going right 1, is what they're saying. Graph g when g of 0 equals 3. Okay, they're using function notation. Identify the slope, y-intercept, and x-intercept of the graph. All right, guys. Now, they're going to talk the talk here, and I want to be able to walk through that talk as well. When they said graph g when g of 0 equals 3, remember that means 0 is your input x, 3 is your output y, even if they call it g of x, but that's an x comma y. That means there's a point on your graph that's 0 comma 3. Hey guys, 0 comma 3 is your y-intercept. When it comes to locating that, we found it. Boom. Now, they said this graph also, and this isn't a contextual problem, they just gave it a description, but they said, the dependent variable increases 3 units. So every time we go up 3 units, 1, 2, 3, we go right 1 unit. 1. Boom. Up 3 over 1. That's a new point that's on your graph here. They rise 3, they run 1, boom, that's a point. They happen to go down 3 and left 1 as well to get a point. They showed that one. I don't know why they chose that direction. I guess to get the x-intercept, right? But I'm going to go both directions, and I'll find the x-intercept as well. So what do we need to find? We need to find the y-intercept, the x-intercept, and the slope. The y-intercept is 3. That was g of 0 equals 3 when x is 0, y is 3. Through our graph, we found out the x-intercept is negative 1. And the slope is that rise of 3 over run of 1. It's 3 over 1. You can write it as 3 or 3 over 1. Either is accepted. Honestly, I believe both are fine. If you saw like an answer key, you'd probably see 3. You just got to know that it means 3 over 1. Okay, there's the answers right there. Solving real life problems. Okay, the last one is a verbal description, but it wasn't contextual, right? Now, what's interesting before I move on is I really expected us to see some fraction slopes to talk about rise over run that way, because those are the ones that I just prefer. We'll see. Maybe they don't show up until the actual problem set, which is fine. We'll do them then. Okay, in most real life problems, slope is here's what I said. Slope is interpreted as a rate, such as miles per hour, dollars per hour, people per year. And look, all those represent time on x. So yes, a lot of them that's the rate. The slope is the rate. So when you think slope, you think rate. A submersible that is exploring the ocean floor begins to ascend to the surface. The elevation h in feet of the submersible is modeled by this function here. Notice how they use function notation. That can also represent y, and t can also represent x in this way. But now t is the time in minutes since the submersible began to ascend. They say graph the function and identify its domain and range. Okay, clearly there's a big, massive change in scale here. What I'd probably change the y's by thousands in order to get the points like plotted the way I'd want to here, and x probably doesn't really need to change much at all. Just keep them as 1s, or in this graph they made them as 2s. So whenever we do a graph like this, we're gonna have to be a little creative when it comes to our scaling, or I will have to be, at least for the solution guide set. It says graph the function, identify the domain and range. So listen, this is the y-intercepts, negative 13,000. Negative 13,000 being the y-intercept also means at time 0 we are this many feet below water, basically. That's our elevation below water. And then the 650t, again, h is in feet, time is in minutes. So if 650 also means 650 over 1. I don't see this anywhere, so I'm just going to write it. So m is 650 over 1. That means 650 feet every 1 minute. This is the rate of ascension of the submersible. It's a rise of 650 over 1. Now, if you saw in the previous graphs, we would like count up 1, 2, 3 over 1, up 1, 2, 3 over 1. Well, we're not going to count up 650 over 1 in that our scale for y is a little bit different, right? Our scale for y is looks like by 2,000s, and our scale of x is by 2s. So you have to figure out how you work that 650 bit there. I don't know specifically how they did it for their graph thing, but basically they do their rise over run enough times, up this over that, up this over that. That ends up being their slope, up 650 over 1 in some sort of way, all the way until they reach the sea level, the surface. 20 minutes later, they reach a surface of 0 feet, and it's at a constant increased rate of change. They said identify the domain and range, or interpret them. What did they say? They said, where is it? Identify its domain and range. The domain goes from time 0 to time 20, which is literally a way of saying that the submersible operated across a 20-minute span continuously. So we use compound inequality. And same thing here. The height ascended, right? We don't teleport. It's not. It ascended slowly or otherwise. It ascended continuously from negative 13,000 feet all the way up to 0 feet, the surface. So here's our height. They say the slope is 650. Boom. The y-intercept, or they call it the h-intercept. I'll probably say y-intercept there, is negative 13,000. And then they did some stuff on the graph to make sure that they got to that thing. The scale was kind of weird there. We'll talk about a problem for ourselves when we have to do one for ourselves. Okay, guys, that was a half-hour worth of lecture. I don't know if I know I overspoke, but I don't know if that covered it in greatest detail even, because there are so many different things we can graph. We'll see how many times that they do it. If you're one of those lecture skippers, I'm fine. I'm fine with you. It's totally okay. If you suffered through that, I hope you learned something or went like, I don't know, maybe I did. Now let's see how it goes. Guys, we're going to begin the vocabulary and core concept check numbers 1 through 4, and then we got numbers 5 through 53 to take care of after this. So a little bit to do, probably a lot of graphs as well. Complete the sentence. The blank of a non-vertical line passing through 2 points is the ratio of the rise to the run. I'm going to assume that means the slope. So when we have 2 different points and we want to find out their rise over their run, they say non-vertical because a vertical slopes line is undefined. So otherwise we get to do the rise over the run in that division. What is a constant function? What is the slope of a constant function? A constant function is a function where the y value remains constant. It doesn't change. This is for number 2. A function, wow, I was going to do it again. Where's u? A function whose y value is unchanging. Whose y value is unchanging. The slope, its slope is 0. There's actually, no, I don't want to say this wrong. I kind of want to take a stab at it though. There's a difference between a slope of 0 and no slope. Or maybe not. No slope might mean a slope of 0. I don't want you to confuse 0 with undefined though, basically, right? Slope of 0 is this. No rise over some run. Undefined slope is all rise, no run. Number 3 on writing, what is the slope-intercept form of a linear equation? Explain why this form is called slope-intercept form. Yeah, you know what? We never really got into that. I mean, obviously we did, but I didn't go back to that and say, you see? It's y equals mx plus b. It's called slope-intercept form because the 2 values that we utilize here to make our graphs are based off this and this. Now, m represents the slope and b represents the y-intercept. That's why it's called slope-intercept form. You're given a slope and an intercept. Now, it's very specifically the y-intercept, okay? It's not the x-intercept. There are ways that we can know that based on what happens when x is 0. That's a big part of it, but that's why it's called that. We have the 2 numbers that represent it. Number 4, which one doesn't belong? Which equation does not belong with the other 3? Explain your reasoning. I'm guessing it's based off form, not based off which slope's positive or negative, which slope's a fraction, nothing like that. This is slope-intercept form, this is standard form, this is slope-intercept form, this is slope-intercept form. And by the way, we haven't run into one of these in the lecture portion. They really aren't using a lot of fractions. Are they going to use fractions on slope-intercept form or are they not? I have no idea because I don't see them yet. And now it worries me. I fully expected fractions. Anyway, on this one right here, guys, the y equals mx plus b, the m right here is actually 1. It's actually 1. When you can't see the number, that means it's 1, or negative case is negative 1. When you can't see the x, when the x is gone, that means the slope was 0, and that's a different thing. But these are all slope-intercept form, and that's standard form, which is what we did out of the previous section. So slope-intercept form. And B is standard form. Or just not slope-intercept form. And you can either turn standard form to slope-intercept form like we'll do in this section, or if it was a review or an actual test and you were given that, you could also graph out a standard form. It's going to kind of be your call. All right, guys, we're going to go into the problem set here. Now, it doesn't look like we're going to do the graphs for a little bit. We'll start with the way that they did examples leading into it. So, but get ready for graph paper as needed. But away we go. In exercises 5 through 8, describe the slope of the line, then find the slope. Now, I personally on graphs am going to marry myself to finding the slope based off counting as long as the numbers are clean integers, they're within my window range, things like that. When it comes to tables or other sets of points, and we're going to have plenty of opportunity to do it, I will calculate the slope using its formula. So for number 5, they stated, describe the slope of the line. Our slope goes down as it goes to the right, and it goes up as it goes to the left, but it goes down as it goes to the right. That is the indication of a negative slope. So when I describe it, that's all I'm going to state, negative. They didn't say explain it, I did to you though. Now, what we're going to do with this is also determine the slope, the rise over the run, or in this case to me, the fall over the run, how much we change in y downwards as we change in x to the right. So for this particular graph, I might not copy and paste this each time. I realized that was a little bit of a time suck there. This one here, I'm going down this much and over this much. Whenever I draw these are called slope triangles. I'm going down 1, 2, 3. That's negative. and over 1, 2, 3, 4, 5. That is a slope of negative 3 over 5. The 5 is positive as we run to the right. This fraction cannot reduce. That will be our slope. It was negative. It is negative. I'm good to go. Number 6. Yeah, I'll copy and paste it. Number 6, this graph goes up. The line goes up as we go to the right. That's an indicator of a positive slope. Remember, all graphs go up, and I say that with hyperbole. Horizontal lines do not go up. But this one goes up as well, right? Doesn't make it positive. Because as it goes to the right, it goes down. As this goes to the right, it goes up. So this one has a positive slope. That's my description. Now we are rising from this point to this point here. We're rising 1, 2, 3, 4, and we're running 1, 2, 3. The fact that that point is 4, 3 is completely unrelated to, well, it is actually completely unrelated because this is going up 4 and right 3, whereas this is going right 4 and up 3 from two totally different points. So yeah, that slope of 4/3, again, completely unrelated to the fact that that point is 4 over 3, or 4, 3, I should say. Now 4/3, like I said, you don't write it as 1.3 repeating, you don't write it as 1 1/3, and this can't reduce. 4/3 is the exact answer that you actually want. You do want that one. Now, number 7 is an example of a graph that doesn't go up at all. It doesn't rise, it doesn't run. Excuse me, it does run. It doesn't rise as it runs. So on this one right here, it says describe the slope of the line. Because it doesn't rise, that means there's no change in y. So as we're trying to come up with the slope, the description is the same thing as the answer. This looks like a horizontal, okay, fine, I'll describe it as a horizontal line. The description is a horizontal line, and the slope is 0. Now, if you want to use these specific points from -2, 3 to 2, -3, -2, -3 to 2, -3, we say no rise over a run of 1, 2, 3, 4. 4 to the right, or 4 to the left, doesn't matter. But 0 over 4 is 0, and always, always simplify this to 0. Don't leave it as 0 over 4. Horizontal line, 0. Number 8 looks like we're going back to a negative slope once again because we go down as we go right. And with that in mind, we can count its fall over its run. Let's see if this has any changes in what it does versus the previous kind of problems that we had. In this one here, once again, negative slope. And this one goes down 1, 2, 3, 4 over 1, 2, 3, 4, 5. So this has a slope of -4 over 5, like so. Now, none of these really had fractions that could reduce. We are going to hit those at some point, clearly. Not yet. And yeah, right, so just kind of get ready for a bunch of other things to happen on the problems that we have. Ooh, I'm dehydrated. Okay, in exercises 9 through 12, the points represented by the table lie on a line. Find the slope of the line. Okay, you can choose any 2 points that you'd like. You can choose the first 2, the last 2, the middle 2, the outside 2. You can choose any 2 that you'd like and determine their slope. For the sake of practice, I'm going to choose these numbers over here. Now, when we choose these ones, and I'm going to write them out as ordered pairs, right? I have a point here that's -1, 2. I have a point here that's 3, 4. I want to find the slope between these two things. And this is going to be very common practice to do. Find the slope between 2 points, or the equation of a line between 2 points. That'll get even deeper. We have a slope formula that looks like this. M, the slope, equals y2 minus y1 over x2 minus x1. Is a way of saying find the distance between your two y values by subtracting them. So let's say that this were x1, y1 and x2, y2. I'm going to subtract y2 minus y1 like that, 4 minus 2. 4 minus 2 gets you the distance between 2 and 4, and that is 2. And now I'm dividing this by x2 minus x1. I can do 3 minus, and this is a -1. So we're subtracting -1, which becomes 3 plus 1. Now 3 plus 1 is 4, and this is a perfect example of a fraction that would start reducing. 2 over 4 reduces to 1/2. This is our slope of our graph. Of our line, excuse me. Now, we didn't draw it on a graph, but if you did, you'd be counting that rise of 1, run of 2, things like that, or rise of 2, run of 4, and then reduce it from there. Now, I happened to choose those 2 points. What if I chose these 2? I think you'd get the same result. And what happens if I chose these 2? I'd get the same result, right? Or the outside 2, it would be a bigger fraction to reduce, but the bottom line is you'll always get 1/2 as your slope for number 9, no matter which 2 points you choose. So there's a little open-endedness to what you want to do with it. It's kind of up to you. Number 10, You can see the y's don't change at all. That might hint something to you. Let's just do the first 2 points this time. Let's do -1, -6, and 2, -6. Now, as the y's don't change, and I do y2 minus y1 over, and I'll do x2 minus x1, again, a 2 minus -1, -6 minus -6 becomes -6 plus 6. 2 minus -1 becomes 2 plus 1. -6 plus 6 is 0. 2 plus 1 is 3. I don't care because 0 over 3 is 0. This is a slope of 0 because the y's don't change. That also means it must be a horizontal line, and it is. That's what a slope of 0 does. So that is a slope of 0. This is a slope of 1/2. Those are the first 2 of the set. So remember, on graphs, not a requirement, but on graphs, I counted the slopes. I counted the rise and run. You could theoretically do that on these ones as well. Number 11, the x's don't change. Let's do maybe the outer 2 values, like this one, and this one right here. So let's now choose the points 0, -4, and 0, 8. How much do I rise? How much do I go from -4 to 8? Well, you can do 8 minus -4 to truly figure that one out if you wanted to. Run, 0 minus 0. Well, we know that's 0. 8 minus -4 is 8 plus 4, which is 12. And 12 divided by 0. Is that 0? No, it's not. Division by 0 is undefined. 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 It's a vertical line, not a function. It's an equation. Doesn't have a slope. The slope's undefined. Number 12, which points would you like to choose? I'm going to choose ones that have negatives. Let's do like the second and the last one, something like that, especially if there's something we got to reduce a fraction on. Let's get heavy on this stuff. Now, I've been doing my x1, y1, x2, y2 from left to right. So when I write -3, -5, I've been calling this the x1, y1. And for this next one, I'm calling the x2, y2. I mean, you can swap them. You can call this x2, y2, x1, y1. As long as these are the 2's and these are the 1's, or these are the 1's, these are the 2's. Don't mix and match, right? So now I do y2 minus y1. I'll be doing -5 minus -19. x2 minus x1 is -3 minus -1. -5 minus -19 is -5 plus 19. -3 minus -1 is -3 plus 1. -5 plus 19 is 14. -3 plus 1 is -2. As much as we have this formula and stuff down, we still have to calculate that, right? Now, this reduces to -7 over 1, but you can also, of course, write that as -7. That's just a good reminder that not only are both accepted, because that's really not only are both of these accepted, but you need to know that -7 means -7 over 1 when it comes to graphing them. So that is your slope of that one. That's all we wanted, right? They didn't ask for x-intercepts on any of these or anything like that. Right, okay. Find the slope of the lines. I think I have to refill water here. Let me do this before I move forward. Okay. Number 13. Analyzing a graph. The graph shows the distance y in miles that a bus travels in x hours. Find and interpret the slope of the line. So as I stated from the beginning, well, a couple things. Number one is slope represents a rate. And number two, it doesn't necessarily matter where you start from or where you end at as far as the actual positions. It's just how do those two specifically compare. Now, so on this one here, we're going from this point to this point, which means we're rising here and we're running here. This one is a little harder on a graph to do a count for. Like I said, if the increments aren't there or the window range is weird or the numbers are weird, this might be a little harder to do a count for. We could still do the slope calculation, right? But at the same time, these are sometimes questions I could ask you out loud and you could answer it based on whatever knowledge you have of stuff. Don't memorize a formula is basically what I'm stating. You might learn the formula, you might know it, you might be able to recall it, but don't go, oh shoot, I can't remember it, now I can't do the problem. That's basically what I'm stating. When your slope is a rise over run, I'm asking you, hey guys, how much do you go up from 60 to 120? 60. You go up 60. Guys, how much do you go over from 1 to 2? Come on. 1. You go up 60. Sorry. You go up 60 and you go over 1. That makes the slope of 60. Now, as far as the y2 minus y1 goes, that's 120 minus 60 over 2 minus 1. The distance between these 2 points is the difference between these 2 points. I say this to my classes all the time. Distance is difference. You take a subtraction and you get this. And that's where the numbers come from when we do that formula. This is the slope. They ask you to interpret it. This is how many miles the bus traveled over the course of 1 hour. That's the rate. The bus traveled 60 miles in 1 hour, 60 miles per hour. Oh, that looks small. Hold on. The bus. Let's do that again. I'm going to say 60 miles per hour. 60 miles in 1 hour. Number 14. Analyzing a table. The table shows the amount X in hours of time you spend at a theme park and the admission fee Y in dollars to the park. The points represented by the table lie on a line. Find and interpret the slope of the line. So in this table, you can see that no matter how many hours you're spending at the park, you still spent the same amount of admission. It sounds like it has a gate fee, an entrance fee, that you spent $54.99 to enter the park, and you're staying in the park longer, and things like that. That's just what I'm interpreting there. Now from here, we can do some sort of slope. How much are we changing in Y from one number to the other? Well, 0, right? How much are we changing in X? Depends. You can go from 6 to 8. That's a change of 2. I spent $0 over the course of the last 2 hours. I'm spending $0 per hour, right? When it comes to slope, based on a comparison of the two values, you can state the admission fee is not changing based on time spent in the park. This makes it a constant function. Now, did you spend money? Yes, when you entered the park. But your rate of increase after that is $0. You're not spending any more money. Now, maybe I might buy a hot dog later, but, so far, no. Maybe not to go on rides or anything like that, or look at, watch events. All right, and exercises 15 to 22. Find the slope and the y-intercept of the graph of the linear equation. Now, they're not asking you to graph it. They're asking you to find the slope and the y-intercept. This is all based off y equals mx plus b form. So guys, these will be pretty quick questions here. Based on y equals mx plus b form, m represents our slope, b represents our y-intercept. So this is something we're going to feature pretty much every time we graph. So our slope is m. The slope is -3. We can also write it as -3 over 1. That's a great way to write it. The y-intercept is 2. Which I like to indicate is also the point on the graph that's 0, 2. That's something I'm going to be writing a lot more when we do our actual graphs. But the slope is -3 or -3 over 1. Either is accepted. I want to remind you of the fraction, though, and the y-intercept is 2. Number 16, they're really not doing fractions, are they? I'm very surprised. We'll see if we get any when we actually graph. Y equals 4x minus 7. The slope of this one is 4, or 4 over 1, and the y-intercept is -7. Where plus b is plus -7, so we're adding -7 in that case. You know what? I'm just going to call it 4. Until we actually do the graphs, I'm going to just call them what they are unless it's already a fraction. Or I feel there's importance for me to bring up what it is. Number 17 just says y equals 6x. Now, that's fine, and it is in slope-intercept form, but if you want the true appearance of where's my plus b, if you don't see anything adding with it, that means you're adding 0 to it. That will help reveal what b is for you. So your slope in this case is 6, and your y-intercept is 0. That does mean that when our line goes through the y-axis, it's actually going through the origin as well. It's going through the point 0, 0. Number 18 has the opposite problem. 18 is a constant function. There's no x value that's here. When I see y equals -1, that's like the b value, right? There's no x multiplied there, so there's this mx that's missing. What makes it go missing? The x was multiplied by 0. It's not that it's not there, it's that something kind of affected it and made it invisible. It's multiplied by 0. That's important because that's all about our slope. And we've seen 0 slopes before. Those are horizontal lines. So that's why it's a constant, unchanging function. The y-intercept is -1, and every y value on this graph is -1. Number 19, Numbers 19 through 22 don't begin in slope-intercept form. If you want to answer the question about slope and y-intercept, you got to get it in slope-intercept form. That's just the thing. Even 17 and 18 had a way of getting it in slope-intercept form, but this is actually not written in the right form. So we get y by itself by adding 2x to both sides, and I can say y equals 2x plus 4. Now do you see why I always wanted to front the x in all those ones before? Because this is the appearance of the form that I want to use here, right? So all that practice is paying off. The slope is 2 and the y-intercept is 4. Yeah, we're not graphing. We're just featuring these things here. Number 20, x plus y equals negative 6. Same thing. It's not in slope-intercept form unless y is alone. So solving those literal equations from section 1.5, I think it was, pays off when it comes to these. Remember, these two terms do not combine. The negative x term I can write first, and this term I can write second. This is slope-intercept form, and I see a negative sign in front of the x, but I don't see the number that's multiplying by x. You can't just say it's multiplied by negative. Negative what? Negative 7? Negative 1. Negative 1. So the slope is negative 1. And the y-intercept is negative 6. Okay. Numbers 21 and 22 take a little bit more to solve for y, all depending on which way you want to go about it. Now, I have a preference how to do it on number 21, and I'm going to express it right here. Negative 5x equals 8 minus y. In terms of solving for y, it would take 2 steps anyway, no matter which way I choose. So I'd rather choose the one that's going to get a positive first. Let's add y to both sides, like this. If I add y to both sides, it gets us positive. It gets it on the left side of the equation. But this minus 5x needs to go this way by being added to this side. So these go, these go. Now it becomes y equals, and here's our 8 plus 5x, or 5x plus 8. So that's my preferred way of doing number 21 and getting it by itself. The slope is 5, or 5 over 1. I'm really surprised we don't have fraction y-intercepts. I was almost equally as befuddled when the lecture portion didn't do them, and I'm like, don't worry, the problem set's going to do them. We have to get them somewhere. Clearly in the book somewhere we're going to graph things with fractions. And it's weird that I'm looking forward to fractions. It's because it's one of the easier things to graph. I know that sounds weird. Fraction slopes are one of the easier things to graph. All right, number 22, 0 equals 1 minus 2y plus 14x. Same issue as last problem. Y is not by itself, and I think it makes much more sense to get this y alone over here and make it positive. But it's not quite alone, because it's multiplied by 2. In fact, these two terms are kind of opposite of what I want here. I want my 14x to go first and my 1 to go second, like that. You might say, but Mr. Robinson, I thought 1 was negative. No, this negative is 2y. 1 is positive, right? 1 is positive, 14x is positive. I want to divide both sides by 2. Now, when we divide by 2 here, you could say divide everything by 2, but at the same token, you can divide each one by 2. Right? It's at this stage now that we're in slope-intercept form. We want our terms to be separate from each other, not all divided by one thing. We want to truly see what's the slope value, what's the y-intercept value. So this slope value is 14 over 2. That's 7. It's multiplied by x and plus 1/2. Leave it as 1/2. You could write 0.5, I suppose, as well. This one's a little bit different from what we normally see. I don't like fraction y-intercepts. I like fraction slopes. So I'm not as infatuated of graphing this one. It was the first time we actually see a fraction. It gives me hope that we'll see fraction slopes in a second. So the slope here is 7 over 1, or 7. And the y-intercept is 1/2. 0, 1/2, if you will. Get more water. I think I swallowed down the wrong tube. Hold on. Okay. Let's see if I can continue and survive this. Numbers 23 and 24. Describe and correct the error in finding the slope and the y-intercept of the graph of the equation. All right, the first one says x equals negative 4y, and it says the slope is negative 4 and the y-intercept is 0. I'm with you on the y-intercept. I do believe it's going to be 0 here. But in order to get the full thing on slope and make sure the y-intercept is 0, this equation is not in slope-intercept form. In slope-intercept form. In order to be, so y needs to be alone. Isolated. So we have to divide both sides by -4. And then, and that'll be a fraction slope. Sorry, I got excited. And then that'll be a fraction slope. So, hey guys, I'm going to first do this. I'm going to rewrite this term on this side like that and over like that. Just switch it because I like the y on that side. I'm going to divide both sides by -4. Now, I actually have a few things to say about this. The fraction actually is, I don't have a lot to say about the fraction, but the fact that it is a fraction. Here's the thing. Even in y equals mx plus b form here, right, I still haven't quite answered it. If I leave it like this, if I ask you what the slope was, you might not get it right. I'm going to say that. I'm not blaming you. I'm stating that you might not want to leave it written like this. When you divide something, forget the negative for a second. When you divide something by 4, what is that the same thing as multiplying by? 1/4. So when you're multiplying x by negative, or when you're dividing x by -4, that's the same as multiplying x by -1/4. You want to write it like this. Y equals mx plus b. By the way, plus 0, if you want to write that. This is my m, this is my b. So as far as what the answer is for the slope is -1/4. So yes, you want to write it like that to reveal what it is. They were correct, by the way, on the y-intercept being 0. They weren't wrong, probably for the wrong reason, but that's your true slope. Get it by itself, get it in slope-intercept form, and then you got what you need from there. Anyway, why was I excited about this thing here? I think we're actually going to, I think we are going to deal with fractions. It's probably, they must be happening here later. Number 24, y equals 3x minus 6. Says the slope is 3 and the y-intercept is 6. Looks pretty good. Looks pretty good. Oh yeah, except for that one thing. The y-intercept is -6. Basically, listen, I'm just going to identify it right now. I'm just going to say it. The y-intercept is -6. I mean, I don't know what to correct the error, identify the error and correct it. I did. They said 6. It's -6. That's all I have to say on number 24, and I think and hope you agree. All right, next exercise 25 to 32. Graph the linear equation, identify the x-intercept. So this, honestly, this numbers 25 to 32 is the core set, to me, of the entirety of the section. These are the context-free, in a context-free environment, right? We are using slopes. We are using graphs. We are using slope-intercept form, all that kind of stuff. So this is what this section is all about to me. So I'm going to grab a whole bunch of these. No, that's old. I tried to copy this twice. Why didn't it come over? I tried to copy the graph. Let's see. I'm going to bring this one. There we go. I'm going to bring this one over for every problem that we do. Probably get it down to size to about like that. We don't need a table to graph. You may use one, but I'm not going to. We're going to do it based off the slope and the y-intercept, okay? So number 25, y equals -x plus 7. Here's how I'm going to do it. I'm going to identify the slope. I'm going to write it as m equals. For b, I'm going to write as b equals. The slope, I'm always going to write as a fraction. It's not a requirement, but it will help you. The y-intercept, I'm always going to write as 0, whatever the number is. Again, not a requirement, but it'll help you. At least for these 8 questions. The slope on this one, we saw this before, it's -1, but that also means it's -1/1. The y-intercept is 0, 7. Why am I writing those two things like that? Because we start from the y-intercept, 0, 7. That's a point that is actually on this graph, when x is 0, y is 7. The slope of -1/1 means in slope triangle basis, as we saw, every time this graph falls 1, we run 1 to the right. So I can go down 1, right 1. This is another point that's on this graph. Truly. And down 1, right 1. And down 1, right 1, down 1, right 1, down 1, right 1, down right 1, down right, down right, down right. And this may seem like overkill. How far are you going to go over? Yes. No. How far are you going to go over? I'm going to graph as many points as I can fit. Always. Period. For any graphs that you ever see me do, find my graph videos in IM3 for the crazy graphs that we have. I'm always going to graph as many points as I can fit in my window range. Now, are these the only points I can fit? No. I could also go up and to the left. -1 can also be written as 1 over -1, can it? Which means you can go up 1 and left 1 and still get more points on this graph. Up 1, left 1, up 1, left 1, up 1, left 1. And this is all the points I could fit on my graph. Now, what do I do from them? It's a continuous function or relation. So I'm going to connect the dots and I'm going to draw arrows at the end of them. Mine already have arrows at the end of them. And that is graph for number 25. Okay. Number 26. Number 26. They do care. We get y equals 1/2 x plus 3. Oh, they do care. Okay. All right. So on this one here, we do have a fraction, y equals 1/2 x plus 3. Now, am I excited for fractions? No, I just expected them, and I was kind of bummed when we didn't have any. Okay, am I excited? Sure. Now, what's your slope? Do not put 1/2 over 1, although you could do that. There's nothing wrong with it. Well, it's weird. Put 1/2. Your slope is 1 over 2. Write it as a fraction. Guys, fractions are good. This says we're going to rise 1 and run 2. That's really nice with that. But where do we start from? A y-intercept of 0, 3. So I will start from this point right here, 0, 3. Again, not 3, 3, not 3, 0. 0, 3. Now, my slope as a fraction, 1 over 2, means I don't have to go up 1/2 to go over 1. I can go up 1, and I can go right 2, and that point is an integer set that's on my graph. I use the fraction to represent a couple 1/2s over 1 as up 1 over 2. Very easy to do. Up 1 over 2, up 1 over 2, up 1 over 2. And it continues in that path. So why are fractions maybe easier than integers? Well, I'll tell you the next time we do an integer problem on number 27. But here's the graph. Why did I go down 1, left 2? Well, 1, it completes the graph, and 2, because 1 over 2 is the same as -1 over -2. I can go down 1, left 2, down 1, left 2, and that still completes it, because, of course, from any of these points, I can also go up 1, left 2. Oh, you know what I didn't do? I didn't identify my x-intercept. So on the last problem, I got to do that. This one I have to as well. This is an x-intercept of -6. And I know you could say -6, 0, whatever, but there's the x-intercept of this one. On number here, this is 7. X-intercept is 7 on number 25. Okay, I wonder why they have us do that. I know why for a word problem, but I wonder what that's all about here. Number 27 has y equals 2x. Y equals 2x. Now, I think we've seen it a couple times, and I'm just going to write it when we get into the problem itself. Y equals 2x. Here's the graph portion. The slope is 2 over 1. The y-intercept is 0, 0. So even if it's not written, we can still identify it. And these aren't required to write down. I think they're just a little helpful for you to start this way with them. In the future, yeah, maybe not. Maybe we won't write them. So we start from here. We start from the origin, which, by the way, that means this is also the x-intercept. Now, your slope is 2 over 1. Why do I write it as a fraction instead of like this? Or why do I express it? Why do I think about it as a fraction? What do you think people could do and mess up with a slope of, if they just said use a slope of 2? Here are one of two things that people might mess up with. They might go up 2 and then just plot the point. And then go up another 2 and plot the point, and up another 2 and plot the point. To the uninformed of undefined and vertical lines like that, or a slope of 3 apparently is the same exact line. That's not how that works. Likewise, they could go up 2, and my personal favorite, over 2. Up 2 over 2, which, by the way, is also the same as up 3 over 3 and up 3 over 3. So that also doesn't work either. 2 over 2 is 1. So when you write 2 over 1, you're reminding yourself that you're rising 2 every time you run 1. $2 per hour, whatever you're talking about. Up 2 over 1. And that's just that good reminder of that. And that any number can also be written as being over 1. I think that's a nice important gesture. And we can also go down and to the left like so. So I always plot as many points as I can fit. This is it. I do need to identify the x-intercept. It's the same as the y-intercept. If the y-intercept is 0, y'all, the x-intercept must be 0. Okay. Number 28 says y equals -x. Clearly lacking in numerical information. That doesn't mean it doesn't exist, though, of course, right? This says y equals -x. Well, we saw this slope before, and we saw this y-intercept before. Now we're kind of putting it together. This slope is -1 over 1, and the y-intercept is 0, 0. So from here, the origin, we will go down 1 over 1 like so, and I'll continue in this path. Now, I understand that's a lot of points to plot. It doesn't take way too long, especially if you talk yourself through it over and over. It's just for precision's sake, making sure that you got what it is you're supposed to get on it. Leave no point untouched. Now, keep in mind for these equations, because we did them with tables so many times, why did we choose going from -2 to 2? I don't know, for variety's sake. But why didn't we choose decimals? Because we don't prefer decimals. That doesn't mean decimal points don't exist on the graph, right? That's why we draw the line. It's continuous. It's continuous. And it has an x-intercept. The x-intercept is 0. Okay, numbers 29 to 32 are not currently in slope-intercept form. Let's get them in the form to graph. Maybe. Do you guys feel comfortable with me not writing these? I'll say them, but just not writing them. I know you can't respond. I'm talking to a camera. Little confession time. During the, because I'm recording this 2024. I already forget what year. So 4 years. Wow, it's 4 years ago. 4 years ago during the pandemic, you know, I was, first of all, I'm subtract 3x from both sides here. I was big on talking to the camera, but I was literally talking to students, right? We were doing distance learning, and that's how I engaged with students. I got so comfortable talking to a camera that when we returned to classes, I had trouble, man. I had not like public speaking trouble, but the eye contact thing. I'm so used to talking to a camera to a wall, and now the space is open. There are people, and I'm like, like that. I don't know. No, I just had eye contact issues, not nerve issues. Hey, guys, I rewrote this in slope-intercept form, okay? Now, as far as slope-intercept form goes, -3 is your slope, or -3 over 1, and -1 is your y-intercept. Y-intercept, not x-intercept. So how do we graph this? We start from -1, and a negative slope should go this direction. So we're going to go down 3, and how far to the right? 1, -3 over 1. So we'll go down 3, right 1, and down 3, right 1. We can also go up 3, left 1. Don't confuse how this negative slope thing works as you go up into the, which direction. Clearly, you just continue the direction of your line. If I go down 3, right 1, will I also go up 3, right 1? No, that doesn't make any sense. Now, this is a different x-intercept though, right? They said identify the x-intercept. Oh, that one's a little weird. How can you guys identify that one? I would try and refrain from trying to do something like guess. But we learned how x-intercepts work. You got to set y equal to 0. So for the x-intercept, let's set y equal to 0. Oh, by the way, well, I'm sorry. We had this form up here, right? We had this form up here. 3x plus y equals -1. Hey, guys, this is standard form. So what's the x-intercept? You set y equal to 0. It says 3x equals -1. Divide both sides by 3. You get x equals -1/3. So your x-intercept is -1/3. So -1/3 comma 0 is it. Maybe you knew that. Maybe you weren't. Maybe you didn't. But yeah, that was in standard forms. That was even easier. But set y equal to 0 and solve. Number 30 is also in standard form, but this x-intercept looks like it's 8. So I don't think I have to do any extra checking on that one. So on number 30, we have x plus 4y equals 8. Now, since it's not in slope-intercept form, then that means that, well, we gotta, to figure out what your slope is or your y-intercept, we gotta get it in that form. So I'm gonna get y by itself. I'm first gonna subtract both sides by x. And then I have -x plus 8. Okay, I'm gonna divide everything by 4. Now we've seen this for this slope bit before, right? Just divide everything by 4 separately. And this equation will now say, if I wanna write it best, y equals mx plus b. My m, I wanna write it as -1/4. -1/4 x plus 8 over 4 is 2. So that's my slope-intercept form equation, and it's gone. There's my slope-intercept form equation for this line. The slope is -1/4, the y-intercept is 2. We start at 0, 2, and now we apply the slope of -1/4. First of all, it goes this direction, and kind of like that path, it goes down 1 and right 4. Yes, fractions. Just count them. Down 1 and right 4. Can't fit anymore. Can't go right 4. Up 1 and left 4. Up 1 and left 4. Draw your line. Identify your x-intercept. What did we say it was going to be? 8? Yes, x-intercept is 8. Now, you might grow a fondness to slope-intercept form. Everybody does. Some people don't like standard form more. It's good that we introduce standard form first just to get you having some liking to it beforehand. I don't know why people don't like standard form, honestly. Listen, both of them are great tableless graphing endeavors. This is technically standard form, just the y is first, the x is second. If I were to rewrite this in slope-intercept form, honestly, I would add y to both sides so I don't have to deal with dividing by -1. Now, because y is positive here, it says 5x equals y. Why don't we just write that as y equals 5x? That looks good. Now, for y equals 5x, remember the slope is 5 over 1. The y-intercept is 0. So we can start from right here. Let's rise 5, run 1. And fall 5, run 1 to the left. And there's our 5 slope. Very steep. One of the very first things that I stated in this section was the slope, the steeper, let's see, which way did I say it? The higher the slope value, the steeper the slope is. This has a slope of 5. Remember the other slope was just 1/4. I know it was negative, but remember 1/4 up 1 over 4? That's not that steep. Remember the slope of 0? No steepness at all. Undefined slope, you're like walking up a wall. Yeah, no, I don't think that's going to happen. All right, and number 32. Number 32 says 2x minus y plus 6 equals 0. Oh, I'm sorry, x-intercept here before we move on. X-intercept is 0. Okay, number 32 says 2x minus y plus 6 equals 0. Once again, I'd rather add y to both sides, and I'm done with respect to slope-intercept form. Y equals, I got 2x plus 6. We're all taken care of, right? We're straight. We got it. So let's go ahead and graph that. A slope of 2 and a y-intercept of 6. I'm going to say it flat out as the numbers are. See if you know what to do with those. A slope of 2 and a y-intercept of 6. A slope of 2. Mr. Robinson, what are you doing? I'm doing my slope of 2, man. And this count goes pretty fast. Once you get pretty good at this, you're like, boom, boom, boom. And you just recognize where those things go. Use your ruler. This is one where maybe you don't have to use a ruler. And I stressed this in the previous section. You don't actually need a ruler, but some sort of straight edge. But you might not need to on these. If you plot all the points downward, then you're probably getting a good straight enough line. But try and use a straight edge if you can. All right, numbers 33 and 34. Graph the function with the given description. Identify the slope, y-intercept, and x-intercept of each graph. I just realized I didn't get the x-intercept here again. It's very likely I'm going to be forgetting some x-intercepts, guys. Especially if it's a contextual problem, I will probably be getting it for you more often. In these questions, I don't seem to as much. Okay, a linear function f models, I'm thinking f of x, models a relationship in which the dependent variable, that's y, decreases 4 units for every 2 units the independent variable increases. That sounds like a slope. The value of the function at 0 is -2. Okay, you know what? Hold on. I'm cheating a little bit. Let's do it this way. Let's write m equals -4 over 2, and f of 0, the function at 0 is -2. So now as an equation, I can write f of x equals -4 over 2 is -2x, and the y-intercept, the value of y when x equals 0, is -2. -2x minus 2. That's the equation. They do ask us to graph it. And oh, listen, they said identify slope and y-intercept. So here's your slope, here's your y-intercept. And let's draw the graph. Okay. I need to adhere to the problem the way it's asked. Otherwise, I'm cheating a little bit there. -2x minus 2. We start here. And now we go down and right. Down 2, right 1. Up 2, left 1. I hope you're drawing arrows on your lines just because I use a line tool here. I hope you can see the arrows on my lines too, by the way. You know, if I make my line thicker and bolder, the arrows accentuate themselves a lot more. Do you see the arrows now? Sorry if I yelled. There. All right, my x-intercept is -1. I felt like when the arrow got big, I had to speak loudly. I'm sorry about that. It's just a natural thing. I'm going to refill this water after this next question. Number 34, a linear function h models a relationship in which the dependent variable increases 1 unit, dependent variable, for every 5 units the independent variable decreases. So on number 34, let's write the m first. M equals the dependent variable increases 1 unit every time the independent decreases 5 units. You can also just write that as negative 1/5 just as a whole, right? The value of the function at 0 is 3. This is an h function. The value of the function at 0 is 3. So here's your slope. This is your y-intercept, like so. I'll just put slope. Slope. Sorry. Okay, so the equation, and it used h, so we're going to say h of x equals, this is negative 1/5 x plus 3. So there's the equation. Slope and y-intercept. Let's sketch the graph. I wish I used this space significantly better than I did. Start at 3, and we go down 1, right 5. Up 1, left 5. Line with arrows. Don't whiff on the points like I did. I'm going to reconnect them. Okay. The x-intercept. Listen, I didn't get to extend my window range farther to see what the x-intercept was. Maybe we can project what it is based on what's happening. We're at 0, 3. We go down to 2 to go right 5. Now we're at, 5, 2. We go down to 1 to go over another 5. We go down to 0 to go another 5. What x-intercept do you think that is? I think it's 15. I think it's 15. Now, if we're not sure, we can go ahead and solve that. But my guess is x-intercept is 15. Okay. Let's find out if that's accurate. How do we find out if the x-intercept is 15? We want to find the value of x when y equals 0. H of x means y. So let's set y equal to 0. Let's do this in green. Let's set y equal to 0. And let's solve for x in this equation. How do you do that? Well, you got to get the x term by itself. I'm going to add 1/5 x to both sides. And now I have 1/5 x equals 3. What if I multiply both sides by 5 to get x by itself? What does x equal? 3 times 5, 15. We have an x-intercept of 15. So even if it falls out of window range, even if it's a weird fraction, you can still substitute 0 for y and solve for x and get your x-intercept. Okay, I'm going to pause and we'll get some more water and I'll be right back. Number 35. Graphing from a verbal description. A linear function r models the growth of your right index fingernail. Okay. The length of the fingernail increases 0.7 millimeters every week. Graph r when r of 0 equals 12. Identify the slope and interpret the y-intercept of the graph. Let's start with the r of 0 equals 12. That is your y-intercept. Did they say graph this? Graph it. Okay. So we're going to have to graph this. Now this would be out of our window range generally because my graph goes from, like 0 to 10 and things like that. We would change scales, but okay, so I will. I'll change scales. I also want to talk about the slope. This slope says 0.7. Now that's a decimal. We're normally seeing fractions, so we can talk about rise over run. Well, you're like, well, Mr. Robinson, you could write any number as a fraction if you just put it over 1. Well, you could, but that's still a decimal. You got to rise 0.7 as you run 1, which is kind of awkward. Now, if you multiply both of these by 10, then you have 7 over 10. 7 over 10 is 0.7, so this is the fraction equivalent. So that's good. We can use that. The thing you got to be careful with, and this is where I got to... thing you got to be careful with is if you use your right here, copy, paste. If you change your scale, like on y, I could go by 2s, and this could be 10, and then this could be 12. Okay, actually, let's go by... Let's go by 4s. Now, this will sound weird. I'm going to go up to 20 and 40. And on X, I'm going to do the same thing. Now, I don't care about these parts. You've probably seen me do this before. For the sake of the context of this problem, probably no negative time and no negative millimeters of fingernail length. If I go by 4s here, my y-intercept of 12 will be 4, 8, 12 right here. Now, the reason I'm going by 4s, because you might say, well, Mr. Robinson, how do I go up 7 over 10 this way? Well, you could sort of, right? You go up 7 to 19. 19 is kind of right there, and you can go over 10. This is 4, 8, and that's 10 right there. You can kind of put that point right, well, maybe even a little bit higher. 19 might be more like that even. Like, okay, there's a point. That gets a little weird. You could try it. We can go again, up 7 to 26, right? We're at 12 now. Oh, wait, this is 24. Wait, what is this? 24. Oh, 26 is right here, and over another 10 is at 20, so probably about right there. It's not terrible. And then up another 7 this is 28, this is 32, 33, and over 4, 8, 10 right there. And then up 7 to 40 and over 10 right there, and that's a point. So I kind of did that, and that's fine. That's fine, right? I could do that. There's nothing wrong with that. Here's what I was thinking of doing, though. Because we're going to draw a line anyway, right? And 2 points make a line. I could also count up 7 like this. Up 1, 2, 3, 4, 5, 6, 7, and over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and just get this point right here and draw the same line. You might say, but Mr. Robinson, that's not going up 7 over 10. That's going up from 12 to 40. That's going up 28. You just went up 28, and you went over from 0 to 40. You just went over 40. Well, hey, guys, remember, our slope was 7/10. 7/10 and 28 over 40, they're the same thing, right? This is times 4 and times 4. As long as the scales are the same, you're allowed to kind of count 7 over 10 as you need to, because they are in the same scale, right? They're all in the same family. So these 7/10 didn't really work out very well, and they also wouldn't have worked out very well with the 0.7, so I wasn't really feeling that. But if I did just these two sets, and let's see, just one arrow here and went out this way, that kind of works in my favor. Now, those other points were I did pretty well on those other points as well. I'm going to pat myself on the back. But, yeah, either way that you look at it, you can do a graph like that. It's just a confusing problem when it comes to graph stuff. Now, it said interpret the y-intercept of the graph. So the y-intercept of the graph says that at whatever time you're measuring this, at week 0, you begin measuring your fingernail length because it says 0.7 millimeters every week. Y is still in millimeters, X is in weeks. No matter how I change the scale, it's still that. 12 millimeters. Your finger, well, I don't know if you're measuring it. Are you doing that? What are you doing? A linear, well, you're not measuring it. Your fingernail length begins at 12 millimeters. I can't type this. So that's kind of the interpretation that I'm seeing from that one. It doesn't begin like you're born that way. It's just that's when you measure it. All right, number 36. A linear function M models the amount of milk sold by a farm per month. The amount decreases 500 gallons for every $1 increase in price. Okay, now that was a slope that they just mentioned. And it said decreases, so that was negative. But this is the first time I think we're looking at a run of something that's not time. Negative 500 over 1. This was every $1 increase in price. Okay. So that's not a time thing. That's negative 500 still, by the way. Graph M when M of 0 equals 3,000. That does mean you have a y-intercept of 3,000. So this is your slope. This is your y-intercept. Okay. Identify the slope and interpret the x and y-intercepts of the graph. Oh, did I? Okay, I identified the slope right here. I identified it in the last problem as well. Okay, these are significantly more massive, numbers here, right? But we can definitely go by thousands in some sort of way as well. I can go by 500s each time here. that would put this as 3,000. I could go by, I should probably do that. So this can be 1,000, 2,000, and 3,000. Now, I don't want to change my x's. My x's can go by 1, and that's fine. 4,000 and 5,000. Now, I'm never going up this high. This thing goes down 500 every time it goes over 1. So there's a point that's right here. And then this is going down 500 just like that. Boom. And this is going over 1. Boom, like that. So for me, it's more of a down 1 over 1 just because the scale of my x's didn't change. And I have to do something along those lines. Now, I'm going to halt it right there. And I am going to graph this without arrows, but I am going to connect the dots. This doesn't need to be discrete. This could still be continuous in a way. And I'll explain it. But it says, interpret the x and y intercepts of the graph. Because there is an x-intercept in this one as well, right? This one goes down. So the x-intercept is at, see, there's 0, 300 up here, or 3,000, 0, 3,000 up here, and there's 6, 0 down here. And it is 6. It's not 6,000 or 3,000 or anything like that. So the y-intercept interpretation is that you will sell 500 gallons of milk from your farm or whatever. 3,000. You'll sell 3,000 gallons of milk if you set the price. Wait. If you don't increase your price. If you don't increase your price. The thing is, though, I don't know how much money they set the price at initially. They never said. You will sell 3,000 gallons of milk if you don't increase your price. In a month. It's a lot of milk. The x-intercept says you will not sell any milk. You will not sell any gallons of milk if you increase your price by $6. You will price everybody out. And that's the idea of the continuous thing, right? You don't need to increase your price an entire dollar only. You can increase a fraction of a dollar. You can increase it 20 cents. You still might lose some customers or whatever with that in mind. They're like, I'll go to your competitor. But increase your price of milk by $6, I'm not buying it. They didn't say $6 milk. They said increase it by $6. Maybe it's already at $4. I'm not buying it at 10. So at least not compared to competitors if they keep theirs the same. All right, let's move to number 37, modeling with mathematics. The function shown models the depth d in inches of snow on the ground during the first 9 hours of a snowstorm, where t is the time in hours after the snowstorm begins. Now, they show an equation. I don't know if you see it. It's in the picture. It says d of t, function notation, equals 1/2 t plus 6. It says graph the function and identify its domain and range. This says during the first 9 hours of a snowstorm. So I'm going to sketch a graph. The snowstorm starts at time 0, and that y-intercept of 6 means we got this right here. Now I can go up 1 over 2 several times. There's kind of a trick to this one, though, if I literally just do the up 1 over 2 stuff. First of all, I will go up 1 over 2 to 10. Now, there's a limit in our domain. They said the first 9 hours of a snowstorm. That does mean that if I connected these points right here, I went too far. My hour 9 is right here, halfway between. I should cut off this graph at this point right here. Now, that's a little hard to graph, not just because it's off the window range, but because it doesn't fit the up 1 over 2 mold. I went up 1 over 2 so many times to, oh, I'm sorry, that's not 9, that's 9.5. Let me do that again. I was thinking going by 2s from a previous problem. I don't know why. But it's right here. Move. It's right here instead, right? So we cut the graph off right there, not all the way at 10. Now that one's harder to do, not just because it's outside the window range going up that way, but because I was going up 1 over 2, up 1 over 2, and then I kind of have to go up 1/2 over 1. This time the 1/2 kind of lives up to its name, right? But that's the graph for that right there, and that would be the ending point. So the starting point is at 0, 6. The last point is at 9, what? Well, this point is a 10. This point would have been an 11. So we got to go somewhere between 10 and 11. That's 10 and a half. I'll put 10.5. Now it's contextual. I definitely want to use a decimal for this kind of thing. So when it says graph the function and identify its domain and range. Well, there's the graph. Its domain goes from times 0 to 9. Its range says how much snowfall was there in inches, how much was depth. 6 is the lowest amount in depth, and it goes up to 10.5 inches of snow. Now, this was in hours. This was in inches. That's part A. Part B, interpret the slope and the d-intercept of the graph. D-intercept is y-intercept. The slope states that your snow depth is increasing 1 inch every 2 hours. 1 inch every 2 hours. You can also, not say reduce, but 1/2 is also 0.5. That's half of an inch every 1 hour. You can also state that, right? 1/2 is also 1/2 over 1. So with regard to the slope, the snow's depth is increasing 1 inch every 2 hours, or 1/2 an inch every 1 hour, every hour. As far as the y-intercept or the d-intercept goes, the d-intercept states, shows, indicates, I don't know, that the function shown of snow on the ground during the first, that at the start of the snowstorm, I'll just write that, at the start of a snowstorm, there are 6 inches of snow on the ground. Okay, number 38. This, I really slowed down. Like, I'm through the problems, not just like, I've become a slower individual. Just like, I really slowed down on the problems here. Number 38. Modeling with mathematics. The function c of x equals 0.5x plus 70 represents the cost c in dollars of renting a truck from a moving company, where x is the number of miles you drive the truck. So when I'm thinking of this, again, we're talking about rates for slope, right? Your slope is 0.5. Listen, they're going to say interpret the slope, so that's probably something I want to jump into. I don't know, I can jump into after the fact. But when you're thinking of money, $0.5 is also 50 cents. So kind of get ready for talking about something with that later. So cost in dollars, yeah. So, okay, they do say graph the function. So, this can also be written as 1/2 x plus 70. And that's important when it comes to rise over run. The last one was rise over run like this. But this one's a little bit different because this is the 70 in mind. These ones are, listen, these are pretty hard to do because I don't want to change both scales. I guess I'll change both scales. That's fine. Actually, yeah, that's fine. That's fine. We can call this 50 and 100, and therefore 50 and 100. But listen, we have to change both scales if we do this because we want to stick that 1/2 the way that it is. So if this is 70, then we can do this up 1/2 like this. Now, it's not like a snowstorm. There's no end to which we can rise and run this. I mean, there's an end to which I can fit it on the graph. But this can keep going if you want to keep driving miles on the truck rental. So this can keep going that direction. So the domain is any x that's greater than or equal to 0. So the function represents the cost of renting a truck from a moving company. So graph the function, identify its domain and range. Okay, so the domain, yeah, there's no limit on domain. X can be greater than or equal to 0. You can drive as many miles with that truck as you like to, starting from 0. Range, you start by spending $70 on the truck up front. So y is greater than or equal to 70. And listen, I'll put money for both of these. So money there and miles here. Greater than or equal to $70. The minimum you're going to spend is 70, and it's only going to go up from there based on the number of miles that you do. Now, this is another problem where time is not the run on x. Your x is in miles driven. So that's part A. Part B says interpret the slope and the c-intercept of the graph. Let's do that out loud first, then I'll type it after. The 0.5 was fine because, like I said, that does represent money. Every mile X is number of miles. Every mile traveled is another $0.5 added to the rental, or another 50 cents. That's the slope. Every mile adds 50 cents to the overall rental fee. The y-intercept, the c-intercept, is that 70, that upfront cost. You are first charged upfront a flat $70 fee prior to anything else here. So as far as the slope, every mile driven by the rental truck is an additional 50 cents in cost. That's the slope. The c-intercept is there is an upfront rental cost. Isn't upfront's not one word? There's an upfront rental cost of, I feel stupid, of $70. Upfront seems like it should be one word, or hyphenated maybe. Maybe it's hyphenated. Okay, number 39, comparing functions. A linear function models the cost of renting a truck from a moving company. The table shows the cost y in dollars when you drive the truck X miles. Graph the function. Okay, we need 38 for this as well. Graph the function and compare the slope and the y-intercept of the graph with the slope and the c-intercept of the graph in exercise 38. I need my graph from before. Okay, I have this one. I'm going to steal you. And maybe the letter A and the letter R with it. I'm going to steal you guys. Okay, so number 39, let's compare this new one that we're getting to the one that you see right here. So this is number 38. Let's see what number 39 is all about. So we have 0 miles costs $40. So that's the rental. That's the upfront rental fee. They probably charge more per mile. 50 miles costs $80. 60, 70, 80. And 100 miles costs $120. Oh, this is the tricky part. 10, 20. That might be the same there. I think those were an up 1/2 right there together, really. It runs out of room, but it also kind of seems to be that same place. We could actually find that out if we substitute. What was it? 1/2 x plus 70? What's half of 100? 50? 50 plus 70 is 120. So those are at the same place there. So this point, let's kind of indicate that. It's equal on both. That's 100, comma 120. Now they stated, compare the slope and the y-intercept of the graphs. So it doesn't matter if those are the same or not. So the, well, we already saw the previous ones, but number 39, this other rental truck company, or moving company, the moving company in number 39 charges a smaller upfront, 2 words, rental fee of $40, but charges, and here's what we're going to find out. What is its slope? We can find it from the table or the graph. Let's do it from the table. An increase of $40 divided by driving X miles. So their slope is $40 for every 50 miles. That's 4/5, which is 0.8. That's 80 cents per mile. Charges 80 cents for every mile driven. Now, if you wanted to know which one should you use, well, it's based on the number of miles you drive. If you can tell, once you drive 100 miles, they both cost the same amount. Before that, this number 39 moving rental thing would have been a better deal just because the upfront cost wasn't as much. But because that 80 cents per mile, after 100 miles, it starts costing more. So if you're going to drive less than 100 miles, number 39 option. If you're going to drive more than 100 miles, number 38 option. If you're going to drive equal amounts, doesn't matter. Okay, numbers 40 and 41 are error analysis. In 40 and 41, describe and correct the error in graphing the function. This says y plus 1 equals 3x. This is maybe the first time that I see more than one. Oh, never mind. Okay, I see the other. I only see one error. Okay, they kind of subtracted one from both sides. You can't really tell. But they kind of did, because now it says y equals 3x minus 1, and look at that, they do have a y-intercept of -1. So it looks like that's good. So they didn't write that, but they have it. Now their slope is the wrong thing. They did a run of 3 and a rise of 1. They should have done a rise of 1. I just said that wrong. They should have done a rise of 3 and a run of 1. So their slope, they swapped the rise and run and slope. It should be a rise of 3 and a run of 1. Now, they did ask us to correct it. That means we have to graph it. So, they do have the correct y-intercept, right? When you get the equation there by itself. So, y equals 3x minus 1 is the better written form of that equation in slope-intercept form. And here you have a rise of 3 and a run of 1. A rise of 3 and a run of 1 like that. So it's a rather steep slope, especially in comparison to what they put, right? So there you go. That's what it should look like. Oh, but it should be blue. Okay. Number 41. On number 41, negative 4x plus y equals -2. I'm sensing that their slope and their y-intercept are swapped in values. Now, this is one of those ones, once again, where they probably should write it. I'm going to write it over here, but they probably should have it written in slope-intercept form. It looks like they graphed theirs based off slope-intercept form, except they chose to say that their slope was -2 and their y-intercept was 4. Because you can see they started at 0, 4, and then they went down 2 over 1, kind of like that. So they basically swapped their slope and y-intercept. They swapped their slope and y-intercept. Honestly, neither of those things are the most critical errors that I tend to see from students when it comes to graphing. I think that people tend to mess up negative slopes quite often. I think that people tend to place their y-intercepts as x-intercepts. I think it's things like that that tend to happen more often than a swappage of something like that. The run over rise thing, it happens, but you know what actually happens more? And actually, here, let me graph this first. Do you know what actually happens more? Is you start using slope so often, right? Rise over run, y is first, x is second, y is first, x is second, that the next time you plot a point on your graph that's an x comma y, like if I said, hey, plot -5 comma -1, you know where they're going to, well, actually, hold on a second. I don't want to do something that's going to go in the way of the problem. Plot -1 comma 5. You know where they're going to plot it? They're going to go down 1 and over 5 and plot it right there. No. Where's -1 comma 5? It's up here. X is first, y is second. So you know what actually happens more than those things is than the run over rise is people tend to flip the ordered pair because you do so many slopes over this time. Don't take something, and I say this quite often, don't take something that you knew how to do before and change it just because you learned something new. That new learned thing doesn't contradict what we learned before. You know what else? You know, you start to graph those lines y equals and x equals. Y equals are horizontal lines, x equals are vertical lines. Watch the next time you call this the x-axis and you call this the y-axis. Those are mistakes people make. People don't often make this other mistake. They might. That's just not very common. Number 42, mathematical connections. Graph the 4 equations in the same coordinate plane. Okay, so, all right, we're going to graph them. Because we're in the slope-intercept form section, I think it makes most sense to put it in slope-intercept form. There may be better versions to put them in, but we're in that section, and I think it's just worth it. So let's just do them one at a time. I'm going to use different colors as well. So I've 3y equals -x minus 3. I'm going to divide everything by 3 here. -x over 3 can also be rewritten as -1/3 x, and -3 over 3 is also -1. Now, I'm going to do these graphs rather quickly, guys. This is 4 different graphs in one. So down 1, right 3, like so. And up 1, left 3. And no, we don't have to label x-intercepts or anything of that sort. But we do have to draw the lines, because we're going to answer questions based off these. Next one we'll do is green. So we'll do 2y minus 14. I'm glad they're embracing the fraction now. Equals 4x. If I add 14 to both sides to get the 2y by itself, I get this. Now to get y by itself, I have to divide everything by 2. And these numbers divide evenly by 2, where we get y equals 2x plus 7. So 7's here. Now I can go up 2 over 1 just once before I run out of room. After that, I really got to go down 2, left 1 like this. So there's the second one. The third one is, and hopefully you'll be able to see these and not get cut off from it too much. 4x, I'm just doing them in different colors like this, hope that's okay. Minus 3 minus y equals 0. Let's just add the y over to this side, make it positive. Now it's y equals. So this can say y equals 4x minus 3. So I have a negative 3 here. Negative 1, 2, 3. And up 4 over 1. Like so. Oh, and down 4 over 1. Okay. And the last one. Oh, you know what else people mess up on is they just screw up counting their slope numbers. You go up 4 over 1 a couple times. The next time you accidentally go up 3 over 1. And then you try and force fit the points when you didn't plot and count the points correctly. That can very much happen. So I see a lot more things happen than what the error thing showed. Okay, x minus 12 equals negative 3y. Now I am but one step away from getting y by itself, even though it's kind of written on that left side, but we can still do this here. And I can rewrite this as y equals, and that's negative 1/3 x, and that's plus 4. So I have a plus 4 right here, and I'm going down 1 over 3. Down 1 over 3 like this. And up 1 left 3. And I think I'm counting mine by the right amounts there each time. If I make a mistake, I'll notice when I draw the line there. Okay, those are the 4 lines. Part A. What enclosed shape do you think the lines form? Explain. Some sort of quadrilateral. Oh, you know what? I know what it is. Now, I don't know if there's a specific one to it. I think it's a trapezoid. I think it's a trapezoid because these two lines are parallel to each other. I don't know how much we're supposed to know about the words parallel versus not, but whether you look at it on the graph, I looked at my equations. You see this equation here with this slope and this equation with this slope? They have the same slope, therefore they run on the exact same path, down and over, down 1 over 3. Being parallel means that. So I believe, so part A, this is a trapezoid. I don't know if it's an isosceles trapezoid, but it's a trapezoid. One pair of parallel sides because same slope. All right, use all this room. I don't know how to answer part B. Part B, write a conjecture about the equations of parallel lines. Okay, so conjecture. Parallel lines have the same slope. Am I right? Yes. Parallel lines have the same slope, but are different lines. You don't want to have the exact same line, otherwise they're not parallel. They're just the same thing. And you can see here through the graph, right? They're running the exact same. These two will never intersect with each other. That blue and that kind of reddish color, they will never intersect with each other. That was part B. Sorry if I'm not labeling them. Number 43. I'm very aware I'm not labeling them. I'm just saying I'm moving on. Too lazy. The graph shows the relationship between the width y and the length x of a rectangle in inches. So x is rectangle. The perimeter of a second rectangle is 10 inches less than the perimeter of the first rectangle. Graph the relationship between the width and length of the second rectangle. Should I just use their graph? I don't know if it works. Let me I have to read the information again. I kind of got lost in the info. So on number 43, we have a first rectangle's information here. Now, let's first just make sense of their graph with their information and see what's going on. They said y equals 20 minus x. Now, that's also y equals negative x plus 20, which is a slope of negative 1 and a y-intercept of 20. Now, this scale is by 4s, which means this is going down 4 over 4, which is the same thing as going down 1 over 1. So to be that slope actually still makes sense. From 20 down to 20 here. If you notice that they put open circles on these because you can't actually have a 0 length or a 0 width. So they're saying it can get as close to there but not actually be 0. Now they said the perimeter of a second rectangle is 10 inches less than the perimeter of the first rectangle. Okay, let's talk the perimeter of the first rectangle here. Whatever what's y? The width? So your perimeter of your first rectangle takes the 2 widths plus the 2 lengths. Now, your 2y can also be 2 times 20 minus x. That's another way you can interpret that width. So by substitution and then distribution, you can have 40 minus 2x plus 2x. Negative 2x plus 2x is 0, so your perimeter is 40. Your perimeter of your first rectangle is 40, no matter what the width and length are, just because of their relationship. It says the perimeter of a second rectangle is 10 inches less than the perimeter of the first rectangle. Perimeter of this one is 30. Do we keep the same slope for this one? I guess so. So if the perimeter is 30, do we get to do I'm thinking about it. Because this hits 20 here, do we just get to take half of it? I'm guessing we get to go to 15 on the next one. It says graph the relationship between width and length of the second one, because they can each be, yeah, because there are two of each of them, right? Perimeter of those, there are 2 of them. So for this next one, the perimeter of that one's 30, and you would be doubling both of your lengths and your widths together and adding them together. I probably need to make a new graph. I can fit it on here. The only problem is I got to use 15. This is 12, and the y-intercept here is 15. 15. And then this will still have that down 1 over 1 kind of relationship. It'll just be a kind of weird looking. Oh, and these need to have open circles as well. So I need open circles on these guys, 15 and 15. 15 and 15 like that. And honestly, it's kind of just having that connection there. I'm going to try and force fit like a down 1 over 1 like this. And down 1 over 1. And down 1 over 1. And then it kind of just hits that other one. So I'm force fitting this graph into this one. Kind of like that. How does the graph in part A compare to the graph shown? They're parallel. The slopes are the same. They both contain open circles. I have to sneeze. Excuse me. And contain open circles. Do you guys know why the open circles are there? I stated it. You can't have a length of 0. You can't have a width of 0. You can have a length of 0.1 or something like that. But you can't have a length of 0. So the open circles are representing the fact it can't be 0. It can get very close to it. So the slopes are the same and contain open circles, but are closer to the origin. Than the previous graph. Yeah, if this one has a perimeter of 30, that's 3/4 the perimeters of 40, and 15 is 3/4 that of 20. So all that seems to make sense of how it is. Okay, number 44. How far are we going to? 53. So 10 more problems. The graph shows the relationship between the base length x and the side length of 2 equal sides y of an isosceles triangle in meters. Guys, an isosceles triangle has two... I can actually have a figure for this. It has two sides of the same length, like these two sides of the same length, boom, whatever, like that. So this could be an isosceles triangle here. These two are equal in length right there. And the angles are also equal in length, but we're talking about base length. The graph shows the relationship between the base length x and the side length of two equal sides y of an isosceles triangle in meters. The perimeter of a second isosceles triangle is 8 meters more than the perimeter of the first triangle. So the perimeter of this one is 2 of the y's plus this x, and y equals 6 minus 1/2 x. So if I substitute 6 minus 1/2 x in for y in this equation, it's 2 times 6 minus 1/2 x plus x. 2 times 6 is 12. 2 times negative 1/2 x is negative 1x. Negative x plus x, it's 12. Negative x plus x is 0, so you're left with 12 for the first perimeter. The second perimeter is 8 meters more than this first perimeter. So that's perimeter of object 1. Perimeter of object 2 is 12 plus 8, which is 20. Now it says graph the relationship between the base length and the side length of the second triangle. This is where I lose myself a little bit on this part. Previous one made a lot more sense for us to do it, and I don't know if this other graph will quite relate as well. I can try. I feel like you can kind of go a little farther out. So let's get a graph paper, copy and paste it. I'm gonna have to play with the scaling, but I need to come up with how much bigger these values can get. The perimeter. Okay, here's what I'm thinking, because the last time it worked out this way. The last one had a perimeter of 30 compared to, wait, where'd it go? Oh, it's up here. The new one had a perimeter of 30 compared to that of 40. That was 30 out of 40 of its size, 3/4, 75%. This one has a perimeter of 20, and perimeter of the second one out of the perimeter of the first one is 20 out of 12, which reduces to 5/3. So it's 5/3 the size in every which way. Whatever this graph has here, we can make it 5/3 times bigger. If this was 2, 4, 6 before, what's 5/3 of 6? 10. The new y-intercept can go up 5/3 bigger, which is 10. This 12 can go 5/3 bigger, which is 20. We just saw 20 over 12. So it can be that as well. So if I use this graph here, I can turn this into 20, this into 10. Same thing here. Do I want to do that? Yes, I do. 10 and 20. So this can be 5/3 of 6, which is, well, just 10. But that's okay. Let's leave it like that. 10. Open circle. And then this goes to 20 here because 5/3 of that, and I'll just connect the line like that. Now the slope should be the same in that same light as the previous set. So 5/3 times 6 is 10. And 5/3 of 12 is 20. So 10 and 20. How does the graph in part A compare to the graph shown? So for this part B, it's kind of the same thing as the previous one, only now those points are farther out. Slopes are the same. I mean, I didn't exactly calculate them, but they should because it's just a proportional growth. So slopes are the same and also contain open circles, but are 5/3 farther from the origin than the previous graph. Okay. Okay, let's go to number 45. Analyzing equations. Determine which of the equations could be represented by each graph. Okay, this is one where I'm going to show very little work in comparison. I'm going to write A, B, C, D, and I'm going to write the equation that I think should go with it. There are 8 equations here, and there are only 4 graphs here, so there might be more than one answer. Okay, what are we looking for? We're really looking for the sign of the slope and the sign of the y-intercept. Like, this has a positive slope and a positive y-intercept. So which ones can have that? No, 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 yes. So just this one, y equals 1/3 x plus 5. A could only be y equals 1/3 x plus 5. Does anything else have a positive slope and positive y-intercept? No. I think all of them actually have different things, right? So A can only be that one. B has a positive slope and a negative y-intercept. So which ones can work there? No, 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 yes. So y equals negative 2x minus, or 2x minus 4, excuse me. And what else? Yes, this one here, 7/4 x minus 1/4. And I think that's it. Part C, because neither of these have that. Part C has a negative slope and a positive y-intercept. So yes, this one, y equals negative 3x plus 8. And I think that's it. This one has a 0 y-intercept, and that's not indicated there. Part D, so it doesn't look like everything's going to be selected. Negative slope and negative y-intercept. That would be this one, negative x minus 4/3, and this one, negative 4x minus 9. So y equals negative x minus 4/3, and y equals negative 4x minus 9. This equation crosses at the origin. I don't see any of these cross at the origin. This one is a horizontal line. I don't see any horizontal lines. And it would be at above the y-axis as well. Number 46, making an argument. Your friend says that you can write the equation of any line in slope-intercept form. Is your friend correct? Explain your reasoning. Any line? Yes. Oh, excuse me. Any line? No. Any linear function? Yes. Any line? No. Not vertical lines. So my friend is incorrect because vertical lines are an exception to being able to be written in slope-intercept form. And this is something we probably have to start detailing a little bit more, right? Horizontal lines are of the kind like the y equals 6, right? You just saw this y equals 6 up here. That's a horizontal line. Horizontal lines can be written in slope-intercept form. That would be y equals 0x plus 6. That would be horizontal with the slope of 0. Undefined slopes can't be used in slope-intercept form. They have a different kind of form that's x equals 7. That's a vertical line. I can't write that in slope-intercept form. There's no y in it. Slope-intercept form literally needs y equals mx plus b or whatever. The x is allowed to go away. The y really isn't. Okay, so vertical lines have that in comparison. Now, everything else would have gone on point. Sorry, I should have moved this thing down. Everything else, every other line works. Vertical lines do not. Okay. All right, let's go to number 47. By the way, x equals equations don't have y-intercepts unless it's on the y-axis, but even then, it still can't be written in the form. Write the definition of the slope of a line in two different ways. Okay. The slope of a line is the rise over the run between 2 points on a graph. And the slope of the line, or the slope of a line, is the rate of change between two values. I don't know if that works, but I like to think about the rate because I like to think of like word problems, right? When I'm thinking $8 per hour or whatever. That's what it is. All right, number 48. Your family goes on vacation to a beach 300 miles from your house. You reach your destination 6 hours after departing. Draw a graph that describes your trip. Explain what each part of your graph represents. I honestly read it and I was not paying attention to what I read, so I'm going to read it again. Your family goes on a vacation to a beach 300 miles from your house. You reach your destination 6 hours after departing. Okay. I don't know if this is one where you have to go like straight into the set, like you have to go straight from home kind of thing, because it says each part of your graph, because like we can do different things. Your family goes on vacation to a beach 300 miles from your house. So let's call this 300, because why not? That means this is going up every 30. So this is 150, etc. These x's are just going by ones. So we're going to reach it here. There's a point that's 6, 300 on this. Draw a graph that describes your trip. Explain where each part of your graph represents. Okay, here, let's just make up some kind of, stuffy stuff. So we're going to start from home, but we're going to do something at this stage right here. Then we're going to have a little breaky break, and then we're going to continue our path. So here's what's going on for my trip. I got a point right here. I got 4 points, sort of, and then like 4 segments. Segment A, segment B, segment C. On segment A, I'm driving 150 miles in 2 hours. 150 miles in 2 hours, which is 75 miles per hour. Part B, we stop for 2 hours. Right? We stop. We haven't increased our thing at all, but time's going on. We stop for 2 hours to eat and stuff. And then part C, I believe that's another 150 in 2 hours. So mine was a little bit boring. Drive another 75 miles per hour for 2 more hours. There you go. You can make some great time there. Takes you 6 hours to go 300 miles with a 2 hour stop in between. Number 49. The graphs of the functions g of x equals 6x plus a and h of x equals 2x plus b, where a and b are constants, are shown. They intersect at the point PQ. A, label the graphs of g and h. Okay, g of x equals 6x plus a. 6 is a greater slope than this h of x2. Larger number means steeper slope. This will be your g of x equation. And by the way, actually, first of all, let me copy and paste this. By the way, this is a great reason, and you know what? We've probably had a lot more graphs like this, and I honestly haven't been paying attention if it has. This is one of the great reasons to use function notation. To have 2 different y's represented in the same graph. Here's g of x, the function representing all the y's based off the x's that we have here. Sharper slope, steeper slope. And then h of x is going to be this one, less steep slope. But they're both 2 different y values represented on the same graph. So we don't have to call them y this, y that, y1, y2, or just y and y. So label them. What do a and b represent? Well, they represent y-intercepts. So a is done. So part B. A and B represent the y-intercepts. That's slope-intercept form. Part C, starting at the point PQ, trace the graph of G until you get to the point with the x-coordinate P plus 2. P plus 2 is 2 more than P is right now. So we trace it over here, and boom, we get to this point that's P plus 2, okay? Mark this point C, okay? Do the same with the graph of H, mark this point D. So we're going to P plus 2 units over on both of these. This is a totally made up thing, right? It's arbitrary. So, but P plus 2 is the same X value for both of these. And I'm going to mark this point D. How much greater is the Y coordinate of point C than the Y coordinate of point D? Okay, this is interesting. So remember, they start at the same point P comma Q. From there, P plus 2 means an additional 2 of an increase here. Let's see, I'm trying to think of the best way, because I know the answer, but I'm trying to think of the best way to state it that will use like an algebraic form. And we can speak logically on it, but I'm trying to think what I should say about the Q's. You know, best I'm going to say is this. Every time x increases by 1, oh, you know what? I'll make a table. So we have x, we have g of x, and we have h of x. Okay, perfect. So when x is p, g of x is q, and h of x is q. Now, every time x increases by 1, like this one here, g of x is going to increase another 6. Up 6 over 1. H of x is going to increase by 2. Up 2 over there. Now, I didn't actually increase by 6. You take your q and you add 6 to it. You're going to find out the q is not going to matter. You take the q and you add 2 to it. When I do p plus 2, the next time x increases by 2, you increase another 6, and here you increase another 2. What's the difference between q plus 12 and q plus 4? I mean, we're making it pretty more complicated than it needs to be because the q's won't matter. You can notice if I distribute this negative into both of these q's, I have q plus 12 minus q minus 4. Q minus q is 0, and 12 minus 4 is 8. So how far apart? Where is it? How much greater is the y-coordinate of point C than the one on point D? It's 8 larger. It's 8 larger. 8 higher up. So the q doesn't matter because they started at the same place, but the p plus 1 and p plus 2 gave you an example of we're 2 farther away from p than we were before. This is 12 farther away from q, 4 farther away from q. They're 8 away from each other. Is that the last point? Okay. All right, number 50. How do you see it? You commute to school by walking and riding a bus. The graph represents your commute. So at least this is going to be kind of like the family trip one, right? There's a start and a stop, things like that. Describe your commute in words. Okay, so the way that I see it, I think I'm walking to the bus stop. It says walking, riding bus, and then I think I stop at the bus stop for a while, and then I ride the bus to school. So here's my thought. I walk to the bus stop for 10 minutes. Now, I can even describe the speed. At a speed of, I travel half a mile in 10 minutes, which is 1 mile every 20 minutes. How do I say that? How many miles per minute? I could say if 1 mile in 20 minutes, that's also in 60 minutes is 3 miles. I could say 3 miles per hour. 3 miles per hour. Where's E? Per hour. Okay. Now what next? I wait at the bus stop. From time 10 to time 14 for 4 minutes. And then, it's like fan fiction. The bus takes me to school. I'm going from the half-mile mark to the 2.5-mile mark. That's a distance of 2 miles. It takes 4 minutes to do that. We travel 2 miles in 4 minutes, which is the same as there's 60 minutes in a mile in an hour. So if I multiply by 15, that's 30 miles per hour. But for 4 minutes. So there it is. I'm trying to bullet point that one. If I thought about how I wanted to write it, I could have written it better, but that's very fulfilling. Calculate and interpret the slopes of the different parts of the graph. Oh, I just did that. So part B, so I over-explained on part A, and I should have read it. So 30 miles per hour, this is bus. 3 miles per hour, this is walking. Now, sitting at the bus stop, I wait at the bus stop for 4 minutes. That's 0 miles per hour, right? That's why I'm sitting at the bus. That's why I said I sit at the bus stop, because my distance hasn't increased and I'm going to take the bus. I think that's what makes sense there, and that's my interpretation of that one. Okay, number 51 and 52. Find the value of k so that the graph of the equation has the given slope or y-intercept. So for number 51, it says y equals 4kx minus 5 and m equals 1/2. This is a good time to remind you again, guys, that slopes do not contain x. They just multiply by an x to affect the rate, times the amount of time or the amount of whatever that you're going to do with it. So your slope itself is just 4k. 4k equals 1/2. We got to solve for k. So I'm going to divide by 4. But how else can you divide by 4? Multiply by 1/4. Why do I say that? Because this has a 1/2 on that side. And 1/2 times 1/4 is 1/8. That is number 51. Number 52 is all about that y-intercept because this doesn't have a k on the slope portion. This says y equals negative 1/3 x plus 5/6 k. And it says your b, oh yeah, and plus right here, b is negative 10. So we need 5/6 k to equal negative 10. And we need to write it correctly. What did I just do? I hate when this it undoes more than I want it to. 5/6k equals negative 10. We can multiply both sides by 6/5 to undo that portion. Negative 10 divided by 5 is negative 2 times 6 is negative 12. That'll be our k value for this one, number 52. And the last question, number 53. Abstract reasoning. To show that the slope of a line is constant, let x1, y1, and x2, y2 be any 2 points on the line y equals mx plus b. Got it. Use the equation of the line to express y1 in terms of x1 and y2 in terms of x2. Then use the slope formula to show that the slope between the points is m. Express y1 in terms of x1. Do they want us to substitute? Oh, hold on. And y2 in terms of x2. Maybe we have to substitute. So, yeah. Oh, well, yeah. No, you know what? Yeah, we do. So, okay, if I have y equals mx plus b, then I can substitute x1 in for x in my equation, and then I multiply it by m, and I add b, and voila, I get y1. Right, that's the idea. That's a point on the right. That's a solution to this thing. If I plug in x1 into this equation, I should get out y1. If I plug in x2 in the equation, I should get out y2. So we have these two equations here. What do they want to say? Use the slope formula to show that the slope between the points is m. Oh, so this, okay. So this is what we can state instead of y2 and y1 like this. So the original slope formula is y2 minus y1 over x2 minus x1. But now we want to use this for y2 and this for y1, etc. So m equals, now I can say y2 minus y1 over x2 minus x1. M equals, now I can distribute the negative here just like I did on the previous question. So it'll be mx2 plus b minus m, that's an x, minus mx1 minus b, because distributing the negative, over x2 minus x1. B minus b is 0, so those parts go away. Now I have m equals mx2 minus, I did it again, mx1 over x2 minus x1. Now, we've done some things on factoring before. Let's see if you can make sense of it here. M is a thing that's multiplying by both x2 and x1 in both these terms. I can factor m out of both terms, and I have x2 minus x1, as if to say m could distribute back into those two and become this. But writing it factored can help us here because it's the same thing on both. And now you see that x2 minus x1 appears on both top and bottom as common factors, so therefore they can divide and become 1, and you're left with m equals m. And that just goes to show that you still get m back out after substituting those two values in, and that's what we get. It's a weirdish kind of question, but of course that's what abstract reasoning is all about, and we reasoned abstractly. Alright guys, that'll do it for this one. This is Mr. Robinson. Thanks so much for watching. Probably the longer of my videos. Not only a long lecture portion, but we really slowed down to a crawl once we hit about the number 30 mark or something along there, I'm sure. I remember it was the next time I wanted to get my water, and things just, the kinds of questions slowed to a crawl. My conversation and thought process might have slowed to a crawl. Honestly, it's a really late night right now that I'm recording this. One of the more important videos as a whole when we were just talking about the things I'm graphing 4 graphs because it's just something that you're going to carry through. You're going to like it a lot. It's going to be that kind of thing like riding a bike that you probably won't forget how to do, which is really nice about it. But anyway, I hope that helped out. Apologies if things didn't work out kind of the way that I planned to when it came to speed and things like that. But, it is what it is. Thank you guys so much. Take care. I'm going to see you in the next one.